The following program is brought to you by Caltech.
The last speaker of this morning session is Matthias Zaldarriaga from Princeton Institute for Advanced Study. And the title of his talk is A View from the Outside. So please.
Okay, thank you very much for the invitation. I'm not so happy that I have to give this talk anymore, but but anyway, I'm thankful for the invitation. I was very happy to respond and say that I was going to come, and since then, maybe I'm less happy. Anyway, so of course, I should start by saying that the BICEP2 experiment that we just heard is just an amazing result. For me, the plot that, when I look, I just cannot believe is this progression of these upper limits and this incredible jump. So it's just incredible. It's incredible. I think believing and seeing these kind of advances is just fantastic. I think the exciting claim of a detection of primordial B modes. I couldn't be happier than that. I was listening for that. I worked on polarization since I was a graduate student. I really like this to be there. It's just fantastic. I really would like m squared phi squared to be true, and I went out and gave a talk at Perimeter after this discovery. I was very happy. Okay, so I don't belong to any other experiment. I want this to be true. Okay, I really want this to be true, and I hope it's true. And please don't walk away with a feeling that I'm claiming it's not for sure. It's not true. Okay, I don't know if it's true, but I will just tell you I'm no longer sure that this is the right interpretation. Okay, and I really admire all my experimentalist friends and colleagues. I really do. I remember, visiting Brian Keating when he was a graduate student working on polarization experiments, when polarization was like a distant. I remember that very well. I was a graduate student doing the theory. He was doing the experiments. I remember the day I saw the plot of Boomerang, of the first peak. I remember where I was. In fact, I was inside of Wayne's office for reasons that I will not say. And I saw that plot for the first time. I mean, it's just fantastic. I'm truly honored to be, a colleague of people like this. But in any case, we just given a result like this, we immediately go and try to interpret it as theories. We just cannot stop ourselves, and it's just unstoppable. And so what has happened since this announcement, apart from the fact that we apparently learned that inflation happened at a very high scale, and there was this super Planckian role of the scalar field, fantastic things. There's also tensions with other data, like as we heard, this tension with Planck, and there's lots of papers about the fact that Planck already was showing deficit power on large angular scales. If you add the gravitational waves, it makes it even more problematic, and there's lots of papers about that. I mean, it's just filled with excitement for all theorists. There's the data, there's tensions, you can come up with your favorite explanation. It's just fantastic. There's a lot of fun speculations regarding this tension, for example. Or maybe there's a big running of the spectral index, something that we could not anticipate in the context of inflation, and it would make little sense, I would say, in the context of low-order inflation. Or maybe there's evidence of the bubble nucleation event of our universe, like some of our friends like to point out. I mean, it's just there's a lot of fun speculation going on, and we all expect that both this tension, for example, is based on two data sets. The Planck numbers might move around a little bit. Maybe the BICEP numbers might move around a little bit because we don't know exactly the contribution from foregrounds. But okay, is this the basic story? Are we debating this tension? Is this a useful thing to be doing at this point? And so I think the first I want to basically discuss the question of whether or not we should think that the B modes seen by BICEP are really cosmological, okay? And I think this started from trying to assign error bars to those foreground models. As you saw from the previous slide, or here, these differences in Planck are just very minuscule things. So this tension is about little details of the data. And so without having some error bars attached to these foreground models, it's difficult to really make a quantitative statement. And so, okay, I mean, that's something that one could try to do. And so let's discuss that. Let's discuss what kind of error bars should we assign to the foreground models, okay? What is our belief on those foreground models? And I think here you can take two possible attitudes. These are the two extremes. I mean, maybe this is not, if you read the paper, BICEP2 paper, this is, it's not exactly what is said there, but I think I came out of the whole movies and stuff like this with the basic impression of the following was, okay, there is a big excess here. Foreground models, I knew, I'm kind of an astrophysicist at some level, are kind of uncertain, but okay, they tried a lot of things, there's a big difference. So sounds good. So let's take as a zeroth approximation that this spread reflects our not understanding of the foreground models. Let's ignore them for a little while. In any case, it's not a big deal. This is the constraints on R, and then we go to the excitement, okay? So this is one possible way. Now, another point of view that one can take is, well, look, we don't really know much about these foreground models, and let's just assume their shape here, which maybe has been determined, at least in brighter patches, by Planck, at some level, at least as presented in this conference we will talk about. And let it become a free parameter. Let's just fit for both things. What do we learn? Then clearly you don't learn very much. This likes foregrounds, you could explain this with dust, and you come up with conclusions just like this, rather than this kind of likelihood for R. If you marginalize over the foregrounds and you let the whole thing just free, then you end up with these kind of constraints. One is the Planck, the old Planck result. Adding the BICEP, leaving the foreground model free is just pretty much the same as it was before. So where do we live? Okay, which one is it? Now, of course, the sane answer to this question is, let's just wait, okay? We will know, Planck will tell us, BICEP has the 100 gigahertz that they've already seen. In fact, we can even start making all kind of sociological interpretations because some of these people, they have seen the data, so why would we be saying this? Okay, we can do that. And it's sane, and on the other hand, I just cannot help it. I just want to know now, okay? If I were, if I just didn't care so much about it, I would just go do something else and wait in a century, we'll know everything about cosmology. Why would we even do anything? We just wait, okay? It's true, in this particular case, it looks like, okay, it's not a century, it's maybe a few months, October, maybe. In any case, I just cannot wait. And there's a lot of people that cannot wait, okay? And so let's try from the outside that we don't have BICEP data, we don't have Planck data. I mean, for the most part, the relevant Planck data we don't have. So in any case, let's try to see what we can say. So you should take it with a grain of salt, okay? Because we don't have this data, but I think some of you at least are interested in the current state, just as I am. They want to know, even if it's just a futile exercise that will, in a few months, disappear into nothingness. But let's see, today, should I think I'm living in this kind of state of knowledge or in this state of knowledge, at least for the outsiders. The insiders know very much better. Planck people, in fact, the frustrating thing is there's probably hundreds of people that know so much, and I don't know, okay? It's very frustrating. In any case, okay, so let's discuss the issue of foregrounds. I think after the BICEP results were announced, it was obvious that there was going to be, from various centers of negative energy, all kinds of throwing stuff, seeing what sticks. It's true. I mean, but okay, in my opinion, some of those things did stick to the wall, and the foregrounds is the one, okay, for me. And I think it was pretty obvious that and I remember chatting with John Kovac and congratulating him and everything, and the next thing I told him, you're ready because your experimentalist friends are going to go after you and try to destroy you, because, I mean, and it's happening, and okay, I don't know what's going to happen in the end, but I mean, it's obvious that people from the outside will try to find loopholes, and I think is the right thing to do. It's progress. I'm not sure I'm happy about the fact that this is on Facebook and Twitter and all of this stuff, but I think it's good. I mean, the bottom line is good. We'll all look at this. We will know better, you know. Yeah, anyway, I have the Twitter feed in the front of me. Anyhow, so, okay, let's discuss foregrounds, okay? So, okay, so I think, so this is kind of what you can find on foregrounds, most of what you can find on foregrounds in the BICEP paper, okay? In fact, of the two models, most of them are things prior to Planck, and we can discuss also the meaning of models in astrophysics, how much one should believe in those things and what they really are. These DDM1 and DDM2 are things that were using by Planck kind of data. This is the explanation of what is actually done to produce these curves that's in the paper. And here there are the four kind of lines of arguments that lend us, and we heard them in the previous talk, that kind of tell us that what we are seeing is actually cosmological. First is the argument, okay, these lines are all quite below, okay? The shape of this curve looks pretty nice. It doesn't look like the shapes of these kind of curves. There's two types of curves here, autocorrelation and cross-correlation, so there's two arguments you can do based on the auto ones or the cross ones. And finally, there are some measures of color, the correlation between 150 gigahertz and 100 gigahertz that can be used to make some statement. So those are the four arguments, and I'll try to go through the outsider's point of view of how I feel about those arguments now, okay? I don't know what will end up, and I hope it's gravitational waves, okay? But I just want to do that exercise. I think the first thing, and I want to say here because it's the most, you know, the bottom line, one bottom line is easy to remember. What's a little bit misleading about this, and it's, you know, it's what we work with, so I'm not saying they are misleading. I'm just saying in doing this comparison, what is a little bit misleading is that our errors enter square in this, okay? So while here it looks like there's quite a big difference, okay? This is the power spectrum. So something that we, for example, might don't know is the polarization fraction of the dust. If you change it by a factor of 2, you change these curves by a factor of 4, okay? That you need to remember. Yeah, okay, good. It's true. The auto ones, which are the dashed ones, you change them by a factor of 4. Okay, the other ones by a factor of 2. So, at least if you look at those curves, I mean, that's just to keep in mind. We are talking about knowing something about this astrophysical process, more or less at the factor of 2. Do we have a knowledge at the factor of 2? Could things be twice as worse? And get us over there, because then we get to square this difference. That's kind of that's where we are. And that's the issue. If this was much below, then we're okay. So as I was saying before, bottom line, we really don't know. We should wait for Planck. But okay, we don't know so much about foregrounds, so not so much information. Nobody has really done an experiment as deep as they have. You know, there's just no detailed information, okay? So, however, Planck has some preliminary results that they have shown in a conference. I attended this conference, and believe me, the one session I never attended was the one about the dust, okay? And I regret this, because some of the talks that I'm going to show you about, I was not there, poor guy, I didn't go, and it's not even recorded, so I don't even know what he said. I just have the slides. So, anyway, so Planck did release something. Those slides were quoted in the BICEP paper. They were used in some fashion. And I think another way of thinking about this, of what I'm presenting, is just some exercise to see if we can reproduce the kind of curves that they produced based on this information that it was presented there. Of course, it's not the best information. It's better to wait, okay? And it's better for Planck to do it. It's better for them to do it. But I'm not part of any of this, and I just want to know, okay? So let's go there and see what we can do. And I think I will divide the extraction of information from these slides into two parts. There's these digitized maps that I will discuss a little bit about, and I really have to thank, that I didn't say in the first transparency, Raphael Flauger, who is down the hall from me at the Institute, and he has digitized this and made an incredible analysis and tried to get the most out of those slides, okay? And I've learned a lot from him, and a lot of the conclusions are based on my discussions with him. But there's also some slides that are just curves, okay? Those are easier to manipulate, so let me just look at some slides. So there was this guy whose name was Amon. I didn't go to his talk, unfortunately, that did the following exercise, because I just want to understand the following. What should I have had expected had I been paying attention to the dust? What should I have had expected for the level of dust in a patch like BICEP? I think that's a fair question. What should I have expected? And there are these slides by this guy, okay? What did he do? He took data from Planck. He measured the power spectrum in various regions of the sky, and he ordered them by how clean these regions were on the basis of the amount of neutral hydrogen measured in some other way. So it's something that is supposed to, with astrophysical type of correlations, map into the amount of dust. And so he had measurements for the cleanest 90% of the sky, 80% of the sky, all the way to 30% of the sky. He had measurements at various frequencies, and so he was able to do measurements and cross correlations and so on, and tell you what he expected for the power spectrum of EE and BB, exactly what we're talking about, okay, exactly what they're talking about, in various patches of the sky. He didn't do the BICEP patch, so unfortunately this I cannot tell you, but okay, other patches. So 143 cross 143, very close to the 150 cross 150 of BICEP. I know they know all of this, right? But I just want to share it in case you don't know. So the first thing that he finds is that this power spectrum in CLEE and CLBB are very well fit by power laws, independent of how clean the patch is. It's always a nice power law. It appears to be always the same slope. He gives you the 143 cross 143 power for a patch that is 70% of the sky, clean as 70% of the sky. But he also then goes and measures patches that are cleaner, okay? So normalized to 90% of the sky, 80% of the sky, 70, 60, all the way to 30, labeled by the amount of dust in the patch, measured independently. I can go into what this is, but it doesn't matter for the purpose of this talk. So, and he found some power law, okay, which he fits and he gives there, okay? So the BICEP patch, of course, is a clean patch. It's much cleaner than any of his measurements. So what I'm going to do now is an extrapolation. Is this correct? I have no idea. But I think based on what we know before and just reading from slides as opposed to maps, it's a decent thing to do. So he has a correlation. You just measure. They tell you exactly how to compute this in different patches of the sky. They give you a map of this dust opacity. You download it. You take more or less the BICEP patch. You see where it lands, around 1.5 times 10 to the 20. Maybe you get 2, maybe 1, something around here. You measure this suppression factor. Their patch should be much cleaner, okay, by a factor of 24. I mean, I'm just digitizing these slides, but this is not. Compared to the heights of digitization that we've learned that we can do, this is... I mean, for all I know, I just printed it big and use a ruler, okay? So that's what you get. So what happens if you do that, okay? If you just take the results from this guy, scale them according to the cleanness of the patch, as we think the BICEP patch is clean, what do we get? And this is what we get, okay? So these are the BICEP points. This is lensing contribution that we already talked about. This line over here is the dust following that procedure. Trivial, it's very easy. Everybody can do it, okay? So that's what you get, okay? If you divide that amount of dust that you get, it's uncertain, okay? I'm not claiming this is the answer. It's uncertain because I'm extrapolating his power law. Of course, this is an average over all the regions of the sky that are as clean as that. Maybe their region is cleaner. There's a lot. Maybe there's noise in them, a lot of things. But, okay. it's uncertain, but this is what if I do this exercise, this is what I get. If I just take his number and divide them by 2 because I'm nice, it's like this, okay? So this is the sum. So this is that scaling divided by 2, added by lensing. And this is the bicep points. So what do I conclude from this, okay? I know it's very uncertain. It's true we should wait for Planck. But I think at this point I conclude that on the basis of what an average patch, as clean as we know the bicep patch is, the level of the signal could be consistent with just being dust. That the level in itself, I think, is not a particularly good argument. Okay, that's what I conclude from this. Again, I'm not saying it's all dust. I'm saying that I cannot know. Okay, so to go a little bit further, I think we need to know. Okay, I'm just doing this scaling based on some patch of, average over larger regions of the sky. Can I say anything about the specific bicep patch? Can an outsider say anything about the specific bicep patch? I think the real answer for this is no, okay? We cannot really say. However, let me go further on this because, following in the steps of the bicep paper, this was done. I just tried to see if I can reproduce it, okay? Or Raphael. Can Raphael reproduce it, okay? So, so what was one of the, so now we need to, the bicep patch somewhere here, you need to go there and see what can we know, okay, about that patch. Is it particularly good? And so it appears that one of the things that was done is to take this map, compute the average polarization fraction in this map, and it ended up being like 5%, which indeed is kind of the expectation on the back of everybody's mind of what the dust could be before we started this discussion. I think if you go look at some document of what CMB Paul can do, it can even be more optimistic than this. So, 5% is a reasonable number. You go measure this map, 5% is a reasonable number. And in fact, as far as I understand, there were two, these DDM1 and DDM2 models that the ones are based on Planck in BICEP. They were produced using 2 maps that were gotten from these S-Lab transparencies. One of them just basically took the average polarization fraction as measured from this and multiplied it by the dust model in intensity and said that's DDM1, that's one of the options. There was another map where they showed directions of polarization in which the separation of the pixels themselves was more like 5 degrees. So the directions now you can get from here, the polarization fraction you can get from there, and you can construct then a template of what you expect there to be in these maps. And we all know that this procedure has a lot of possible complications, and it's not, again, we should wait. But in any case, what possible complications are, well, there's noise in these maps, this DDM1, we are just multiplying by the average polarization, it's not having the polarization fluctuations. This only has the direction about in 5 degree pixels, the direction, how it fluctuates on smaller scales, we don't know. Many things you can, and remember that the errors enter square. But okay, this is an exercise, given this, that you can do. And the exercise gave this curve, okay? And so we tried to check whether we agreed that it gave that check. And the reason we started doing this check, or at least Raphael, my understanding, the reason is that there is this incredible puzzle after we did this, because we took this amount slides, which was the easy thing to do that I just told you, and we got somewhere over here. And suddenly we take these 2 maps and we kind of do the same as they did, and we get somewhere over here. What's going on? Is the Planck itself, these slides, there are slides, they don't even need to be consistent. It's not their public release. But however, is there some inconsistency in the Planck slides? Are we misunderstanding something? What's going on? So, okay, this is what I think is going on. And I think the lesson why I think is important I'll go through this in a little detail, is because I think this is not, from an outsider's point of view, if we want to get our own estimates of the foreground, this line of doing it is not going to work, okay? I want to tell you why I think it's not going to work. The reason so what is this map of? So when we measure polarization, we measure the Stokes parameters Q and U. This is a map of the polarization intensity, okay? The polarization fraction, which is the square root of Q squared plus U squared divided by the intensity, okay? In each pixel, you do that and you make a map of this. And if you average, you get 5%, okay? However, it's a little bit unclear what went into this map, okay? Let me tell you what is unclear about it. First of all, what went in the denominator? So the problem with this, usually in the CMB, we end up usually always talking about fluctuations, okay? But when we make this map, if there is a zero level, it contributes to this ratio. So we now have to care about what was the zero level in these maps, okay? And it turns out, so the average of the intensity, and this has contributions from the dust from the galaxy, from the dust from other galaxies called the cosmic infrared background, and then there are the fluctuations. The cosmic infrared background is supposed to not be polarized, so if you put this in the denominator, then it makes the polarization fraction smaller, okay? Then on the numerator, there's also these monopoles of the Q and U maps, some average Q and U on the entire map. I mean, one needs to understand what was in there for doing this measurement. There's the noise, because you're doing Q squared plus U squared. It needs to be debiased, what kind of errors that introduces. So there's a lot of systematic issues in trying to understand what to go from this map into producing something, okay? And I think in the end of the day, my assessment is that the most difficult thing are the CIB corrections, which I think for this particular map, I believe, I'm not sure, and the people that made the map, they say they don't remember as far as I can understand. But I believe that when this map was made, this CIB correction was in there and lowering the degree of polarization. I'll tell you why I think that. But I also know that the way the average value for the dust and the Q and U are set are using some of these astrophysical correlations that are quite uncertain. And so I think at the end of the day, on the low emission regions, these kind of maps are very unreliable, okay? And I think that's probably the reason why they were masked in the Planck release that came later. It's nothing to do with not showing the BICEP things, but I think it's all to do with these maps being difficult to interpret. So the reason I think the CIB was included in the denominator, making all the polarization fractions smaller, is that we now have a map that was released by Planck outside of these masked regions, where they say exactly what they did, and they didn't put the CIB and so on. And you can look by eye, and you see much redder regions here in the new map than they were in this other map, okay? So, and in fact, Raphael went even further. He digitized these Q and U maps that I will tell you about. He tried to reproduce this and that out of them. He can do it, and the difference appears to be the CIB corrections. So I think by the time if you buy that, I don't know if this is true. I don't know exactly what was done for this, but it seems reasonable, or at least if you look at the difference between those maps in the S-Lab and what has been published later by Planck, that this map is not normalized in the appropriate fashion, and probably the polarization, if you take, if you renormalize, assuming the issue was the CIB, then you discover that the polarization fraction in the BICEP patch, instead of being 5%, is more like 8 or 9%. Just doing the same thing. I don't know if this is the mistake or the issue. I don't know, but it's my best guess of what the issue is. So what happens if you just take the DDM2 auto map, auto spectrum that was presented in the BICEP paper, and you just change the 5% to 8%. It enters squared, the thing goes up. This is that. This is the sum with lensing. These are the data points, okay? So, so my conclusion for this, again, is not that I'm sure it's all dust. And I don't want the Twitter to say this, okay? My conclusion from this is that, that there's no inconsistency in these amount scalings. There's no inconsistency between this 5% that appears to be in the Bernard polarization fraction and the scalings from Amont. There's no inconsistency. It's just what the zero level was in that map, if you account for that, where you end up is right where you end up in the other way. So that's my summary, okay, of that exercise. And again, unfortunately, if you take that, well, the points are not so different from the line. And I think one thing that one needs to keep in mind now is that these points over here, the error bars, are just the detector noise. And the reason what's relevant for ruling out, for r equals to 0 is the detector noise, is that there's no sample variance if there are no B modes, okay? But now if they are B modes from, say, anything, in particular dust, and there's some sample variance of those, one should add to these error bars the sample variance error bars, which are very large. So unless we have a detailed, not just an estimate of the power spectrum level on that patch, but actual modes on that patch that we can cross-correlate, then we have to pay, in order to assess the significance of these, we have to pay the cosmic variance error bar, which I think roughly from reading the paper and so on, in this beam is like, above 50%. It's big. The cosmic variance error bar is big. So if indeed there is such a signal like that, and all that I can tell you is it's rough power, okay, power spectrum, as opposed to in the map, then the error bars that are important for assessing the significance also should include the cosmic variance, and okay, the significance, it will be reduced if that's what is there, okay? Let me maybe should I go into this or not? This issue of the monopoles is not just about the CIB, which is what most people are talking about in the social media. Those polarization maps are difficult to do because, as I was telling you, as far as I understand, and I hope some experimenters can correct me, but how is the zero level of the intensity and polarization maps of Planck determined, the ones that go into the ratio? Well, for example, for the intensity, we know all the details of what they do. They take another channel, the 857 gigahertz channel. They correlate that with the amount of neutral hydrogen, this measure of the dust. They see this typical astrophysical blob, okay? And they say there is some correlation, and let's demand that when there is no neutral hydrogen, if we extrapolate it into some region where there's no galaxy, unfortunately there's nowhere in the sky where there's no galaxy. So let's set the zero levels of the map such that if we made an extrapolation to zero dust according to this correlation, we will actually get zero and not some offset, okay? That's the level. And you can start looking at all of these uncertainties, and you can see this blob. It depends how you cut, high velocity clouds. It's very uncertain, okay? So this, and the same thing is probably true for Q and U maps, but that is not in a Planck paper. So I don't know. So I think this business of doing polarization fraction maps, in addition to scanning, that is not very good that we are doing this, but okay, fine, we're doing it because we want to know the answer. But in addition to this, I don't think it's the way this will get resolved by Planck, or it's not through this mechanism. Even if we have no problem of digitization and stuff like that, it will not be the way, because there are a lot of uncertainties. And because they enter square, it's easy to get factors of 2 in CLBB, no problem. You start adding them. So now, let me just say one other more thing. Going down this path that we shouldn't really be going through, of digitizing stuff and trying to get an answer before the real professionals try to get the real answer. Let me just say that in this SLab meeting, there were some other actual, not just polarization fraction and polarization direction maps, but there were actual Q and U maps also given, okay? So one can decide, this was not done in the BICEP paper, but one can say, okay, let's just do it ourselves, see what happens. I think I'm telling you the story, and Raphael Flauger has done a lot, and he had a talk yesterday in Princeton. You can watch the talk and see all the transparency. I think this exercise is just the poor man's outsider exercise. It's not the right thing to do, but anyway, I'm just telling you anyway, okay? Just what is out there. And there are many reasons, and I'm not saying, there's many reasons that I think it's dangerous to do this. And perhaps the best reason, I mean, I'm not the moral stuff, I don't care. I mean, it's okay, it was published there. If we can use it, we all use it, okay? It's not about that. It's just that if I just go, for example, to some of the Planck papers that were published at the same time, I mean, just as the BICEP team cares a lot about the various systematics and has done a lot of checks and are sure their signal is not systematic, Planck also gave there in some of the infinite number of plots that they showed kind of their best estimate of the systematics at the time. I hope it's much better than this now, but this is kind of what they put out at the time. And same typical kind of bandpass leakages, the things that BICEP worried about and did all these jackknives that we heard about. Levels, estimates of that were given in this plot, and some of them are this band over here. If I just scale according to this NH1, this amount of dust kind of correlation, what kind of power spectrum one should expect in the BICEP patch for the dust at 353, it's somewhere here. Okay, this is my line of PowerPoint there in the thing. You do this estimate. So it's not obvious that those maps are good enough to do this job. Okay, it's not obvious at all. And I'm hopeful and more or less confident that this is much better now for the internal Planck thing. So we will know much more when they release. But we have to work with maps that, in addition to going through some pipeline of Keynote and stuff like this, they might have some systematics that we just don't know. And as it was also mentioned before, the noise level of Planck in polarization is not something that they have published. So we also have to make guesses about that. So very, thing that is not so correct to be doing. But anyhow. So let me summarize what happens if you just go ahead. Forget about it, let me do it, okay? And in fact, the me is really Raphael, okay? So what did he do? He did actual digitization of these Q and U maps, okay? And he tried to estimate the noise of those maps. I can tell you how he did it. There's some noise associated also with the digitization. So he did this ridiculous Monte Carlo in which he made realizations of things. He put it into a GIF file, PDF file, presentation. Then he went back into the GIF file, depending on what you do with the keynote, what happens at the end. All of this is true, okay? But I'm telling you, what happens, are the best guess, okay? It shouldn't, but anyway. So, but I think there are certain interesting things that you learn when you do this exercise. First of all, he managed to, this uncertainty of what was this polarization map of, and I think he can reproduce all of these slides, and so I think one can be fairly confident that this issue of the CIB is indeed the story. Then he also took the masks of Amont, this 90% of the sky, 80% of the sky. He measured the power spectrum and the scaling with NH1, and he reproduced all of this, okay, from those maps. So the maps are not completely crap, okay, but at some level they are crap, okay, and the level it's interesting, it's that level. So other thing that he did, he took those maps and he correlated them with WMAP, and he saw correlations with the synchrotron and so on. So, I mean, it's not a map of simulation, right? There is information, and so I think the bottom line is that the amount extrapolation is reasonable. This is kind of what you get if you measure in bigger patches than BICEP. There's nothing wrong with that. We don't find anything particularly wrong. So, for example, this has the Amont plot. His version of the Amont plot, the lines match. He could even, so as I was telling you, from the Amont plot, what you had, he measured in various regions of the sky, and he fitted this power law. And the cleanest region that he had was 30% of the sky with this kind of level of dust opacity. And the bicep region was around here, so it required quite a big an extrapolation. Okay, so you can even be, you know, brave, and once you reproduce all of these points from Amon, you say, okay, let me take cleaner regions. So he made points for both 20% of the sky and 10% of the sky based on these maps, and they fall more or less in this correlation. But something hopeful is that, and I don't know what this is, if this is a problem with the digitization, I don't know, but something hopeful is they appear to be lying below the Amont extrapolation. So, but they have big error bars, and so we don't really know. But this is like a hopeful sign, I think. They are a little bit below, but of course this will be done correctly later by people that have the actual data. But in any case, if you just take his measurements here or the Amont ones, and he tried to assign some error bars to this kind of extrapolation and so on, these are the data points from BICEP. This is his best range, which is more or less the same as I showed you before. Okay, so I think. And this is done entirely from those Q and U maps. So I think, at least from the point of view of the Amont slice, the polarization fraction maps, and the Q and U maps are given in this SLab meeting. They're all kind of consistent. Okay, we don't know. Hopefully, the answer is right here. The actual dust is in the lower region of this estimate, and everybody's happy. I don't know, but. You know, it could be even quite much higher than the data. Sorry? Oh, yeah, this is the sum. I'm sorry. This is the sum of the measurement of dust plus the lensing. That's why it's going up. Okay, I'm sorry. Yeah. So this is actually even more ridiculous, I would say. I shouldn't use, poor Raphael, he stayed for a long time doing this, and he continues to do it. And so anyway, this is, you know, you go all the way, okay? You just say, I believe this. I do my hill picks to give to PDF, to hill pick simulations, Monte Carlos. I do for noise. I do for synchrotron. I do for CMB. I try to, their artifacts, try to measure some transfer function, correct for them, and so on. And then now I measure, take the bicep patch, more or less, at the best one can guess from the published, and measure in this procedure the dust in that region, and it comes out, and most of it is it comes out between these two, and this big range is just because that region there's noise in the maps that he has to estimate. I can go into details, but it doesn't matter. I mean, it's mainly the uncertainty in the noise, and so, I mean, this is not conclusive, but just to show you. Well, so. What happens when you do that? So okay, let me skip this one. So as far for me, this was a very long way of saying that for me the kind of expected level. I mean, maybe I should not use this word because the expected level before people started discussing this was indeed very low, as it was. But I think a more reasonable assessment of what was presented in the SLab meeting from Planck is that the dust can be consistent with all the signal. Okay, I think that's a fair statement. Maybe this was not what we all expected or hoped for or whatever, but I think a decent reading that has gone through various checks is kind of that's kind of the assessment, I say. So now you're left with the following, with the comparison of 100 versus 150 that they presented, the color of the signal. And we already heard this, that if you fit for the spectral index of the signal, you get this likelihood curve. This is synchrotron, this is dust, this is their best fit, this is the CMB. So this already in the paper is not super significant, but okay, that's a good thing. And so let me see if I try to shoot at this as well. Okay, not because I'm mean. I mean, it's not really. It's just okay. Let me just do it. See what happens. I mean, I get most feedback. Okay. So if I understand it correctly, what was done in the paper is assume that the first 5 band passes first 5 data points in this were all moved together with a single slope, which is called beta. And if it's dust is this, if it's synchrotron is that, if the CMB is that, and then, this is what is done. I think this is not the right, if we are trying to rule out whether it's dust, that's not quite the right calculation to do. And I think when you do that slightly better calculation, I think you would move the significance even lower than this at this point. And the reason, and already was alluded in one of the questions in the previous session, is that there's the lensing, the CMB lensing, that we know it's there, and that has the spectrum of the CMB. And if you are assuming that this is dust plus lensing, which is, I think, the null hypothesis, or maybe dust plus synchrotron plus lensing, that's our null hypothesis, then those spectra tend to go down with L, and the higher points here are mainly have a big contribution from the CMB lensing, okay? Which then would pull the predicted expected spectrum of the null hypothesis closer to the CMB spectrum, okay? So you're not trying to say, oh, it's 100% dust or 100% synchrotron. That's not the boogeyman that we are shooting. The null hypothesis is that it's a combination of dust and synchrotron and CMB lensing, okay? Synchrotron, I think, is much less of a concern, and I will skip now the transparencies I have about synchrotron because I think it's fair that it's much less of a concern, although I'm not convinced that it is an irrelevant concern for this question, because once you go to 100 gigahertz, the synchrotron is up by a factor of 2. So the question really is true, at 150 synchrotron negligible, okay? But given what we know and allowing ourselves some freedom of not knowing the spectral index in the patch and so on, could it be that at 100, when the synchrotron is 2 times bigger than it was at 150, it helps fill out a little bit of the inconsistency that would be there if the entire signal was dust? Because if the entire signal was dust, when you're at 100, it goes down. The signal is expected. So let me back down. So if the signal is CMB, you should get the exact same, and these are the data points at 150. The expectation at 100 gigahertz is just the same, okay? Because let me just say it like that. If it's dust, the points should go down by basically 40% when you go from 150 to 100. Synchrotron, on the other hand, goes up by a factor of 2.5, okay? So if there's a little bit of synchrotron, one question would be, can it fill up a little bit? It will not explain the signal, I don't think. That seems completely unreasonable. But well, no, because it's the auto spectrum, right? You're doing 150 cross 100 in this plot. So I only have that to work with. So here's just this. So sorry. I mean, when you have 100 cos 100, it's much, but again, I don't have. So, okay, and the one thing to say is that, the other thing to say is that when you add dust plus synchrotron, you have to remember that the synchrotron is coming from the same galaxy, so it's not like a random thing that is not correlated. High degree of cross-correlation of the actual map of dust and the map of synchrotron in a patch is not something that we can say is ludicrous. In fact, we probably expect 50% cross-correlation. For example, if you just take the digitized Q and U maps of SLAB, Flauger digitization, cross the W map, very low frequency, 23 gigahertz, you see this level of cross-correlation, which is telling Raphael that he's digitized the map reasonably well, but is also telling us that synchrotron and dust have more or less similar maps, okay? Anyhow, so, okay, let me skip so these are my best guesstimates of what is really the null hypothesis, okay? So these are the BICEP2 100 cross 100 data points fitted by the R of 0.2. If you just take this amount scaling that I told you at the very beginning, you divide it by 2 because it's nice, okay? And you just, this is the prediction. So Okay, I don't know which one is a little bit better, but at 150, this is kind of the null hypothesis, okay? Now, when you go to 100, the contribution from lensing should stay the same because it's CMB. The contribution from dust should go down by 40%, and this is where the curve lands, the dotted dotted red is kind of, I would say, the thing to shoot, okay? And these are the 150 cross 100 BICEP data points. And I don't think one can claim very high significance of saying this is worse than that. I mean, the other way around, this one is worse. Both of them, I think, are reasonable fits. I cannot do a proper job of fitting. I could quote the chi-squares by digitization of these plots. I have them, but I will not say them because they're not the full covariance. Okay, this is another way of showing the same thing. Okay, these are there 100 in the patch, 150 cross 150 points from BICEP2. Okay, let's assume that so that now let's try to make some comparison that doesn't suffer from cosmic variance. So this is actually what's there in the sky in that patch. Okay. So if those modes have the spectrum of CMB, the prediction for 100 cross 150 should be the exact same points. Okay. If I assume it's lensing plus dust and I just rescale the dust, is the blue points. I just take those points and divide and now the question is, are the blue points, what is the chi-square of or the likelihood of the blue points relative to the black points compared to the data points, which are these, okay? And when you stare at these points, you realize that given the size of the error bars, we are talking about the first 2 points. The last 3, they don't really matter too much. Here, of course, big error bar, these 2 points fit the exact same way. This one is up there. These big error bars, these one are quite low, both of them, okay? And this one, very close compared to the error bars. These are the 2 points that matter. And what happens when you try to put some numbers to this comparison is that, I mean, this first point, the measurement, the BICEP, the cross spectrum, the measurement is low compared, so it prefers the dust a little bit. This one is high, it prefers the CMB a little bit. This one is higher than this one is lower, and so you end up preferring the CMB by a little bit. But we're talking about these kind of differences, okay? So I think I take away, unfortunately, that I'm not so convinced that this is, and this is another way of doing the same thing, where the kind of where the spectrum of the null hypothesis would end up if you include the CMB lensing, it would be somewhere there. But okay, so what is my summary, okay? My summary is that, unfortunately, maybe I should have changed the word expected is wrong there, but I think the level, in my humble opinion, okay, the level of the power spectrum of B modes in the BICEP patch, even accounting for the fact that this BICEP patch is very clean, accounting for this using this extrapolation, the best I could gather from these SLab slides, the level is consistent with being dust. It's not, in my opinion, it's not so high that we should for sure rule out this as an insane, unlikely possibility, okay? I think the level is consistent. That doesn't mean I know it's dust. I have no idea, but the level is consistent. I think making a definite statement about that requires going into maps and looking into the actual BICEP patch. As I tried to stress many times, I think nobody can do this at this point correctly, only Planck. We have to wait, and this is the same thing to do. Raphael couldn't help himself, I couldn't help himself, and I'm just reporting this, and I hope I'll get all kind of things thrown at me. But if you just go ahead and go and do what you can with this digitization and so on and so forth, I think this statement kind of stands for me. I mean, all that we know from these different Amon slides, digitization of Q1U map, digitization of P map, it seems consistent. So I think this statement is a fair statement, okay? And once you buy that, if you were to buy that, the strongest part of the argument comes from the frequency scaling, or the color of the signal. I think already in the BICEP paper, this was not so significant. It will get much more significant with the data they already have, and so we will know much better, and I'm all for that. But at the moment, I think this evidence is weak. And especially after you put lensing of the CMB synchrotron, okay, I should remove because I think it's a little bit of a red herring, although the Planck, I mean, it depends on how facetious you want to be, because the noise of the WMAP in that small region is very high. So you can allow very different scalings in that single patch if it's kind of weird in some way. But so that's kind of my summary. Okay, let me not go into this because it's just too depressing. So I think I don't find the case for Primordial being more convincing at this time, and I hope it's just a temporary feeling, okay? More frequencies, Planck, that's definitely needed to settle the issue. I'm very much, you know, but I think, as I tried to argue at the beginning, if we don't have this, I mean, for the ones of us that are interested in the cosmological consequences of this, the moment you allow yourself this amount of freedom that this scaling seems to allow on the level of dust, you cannot make, you know, basically if you run a likelihood code with BICEP plus some foreground marginalization plus Planck drives everything, and you gain the same results that you got with Planck. So getting the actual level of foregrounds in the BICEP patch, the actual map, is crucial, and I hope we will get it from Planck, or we will get the 100 measurements. Until that day, I think I remain skeptical, and I really sincerely look forward to in the end, as I say, we'll wait for Planck, and that will be. I also look forward to being told that these estimates are wrong and that I can get to the conclusion of happiness even faster than that, because I was in this promised land like a month ago, and now I'm not there anymore, right? So if I made a mistake, if it's something wrong, if it's, you know, please, I'm really happy if that's the case. It's truly, that is true. And I just want to say that, you know, I know this, you know, this digitization and so on is not the right, you know, the fully correct procedures. In any case, I've discussed a lot with Raphael. I think I really admire him. I'm very happy of what he has done. I think it's great that somebody can drop everything that they were doing to try to, you know, get the best possible outside, you know, analysis of what it is that we even knowing that this analysis is, you know, flawed because of all of these systematics, and that in a month or two we will know much better. You know, it's true that maybe we should all wait, but on the other hand, I think one should take the positive view that this is our new way of refereeing, okay? We are not refereeing this in the standard way. There used to be a time when everybody sent things to the journals before they put it to AstroPH. For theorists, this, I don't know, I didn't even exist when this was the case. For experimentalists, it took, you know, they were doing this. Now we don't do it anymore. Nobody does this. We put on AstroPH, and we do the refereeing like in the open, okay? This has the good part, the bad part, but I think it's a fact, okay? So I think it takes people to drop their stuff without even required. They're not even getting a referee, you know, a letter from some editor asking anything. And they're spending a lot of time, like doing the best they possibly could to raise questions, to make those papers better, to make our understanding, just as the referee of any paper is supposed to be doing. And I think that's great. I really, you know, want to, you know, thank Raphael, because, you know, he put a lot of work on this, and he informed, you know, all of my opinions. So anyway, that's
So thank you very much. So any questions, comments, or refutations?
So first of all, you're a real downer, Matthias.
What?
You're a real downer.
I'm sorry. And,
So I have
you know,
one
Raphael had you know, he gave this talk in Princeton. The audience is different. He sent me here, and I had to, you know, look how great things, and Andrew Lang, who I really admire, and then I'm here, what I'm going to say anyhow. But
So I just have one question, clarification. So there's this polarization to intensity fraction, which we don't know, And if we double it, then the auto power spectrum goes up by a factor of 2. When I do the cross-correlation analysis, though, doesn't the uncertainty in the polarization fraction disappear?
Yes, this is a great question, and I didn't want to go too much into this because I don't have a fully definite answer. But let me tell you what I know about this. So so I think it is the case that naively it is the case, or that if you were to do the cross correlation. Then first of all, the uncertainty is being 4 is just 2. And then the fact that, you don't see an actual cross-correlation between the BICEP map and this template seems to be very good because there's just no match. So what's going on, okay? So, so those seem to be very good positive things in the positive direction. Now, unfortunately, I'm not so sure about this because of the following reason. These templates do not have information about the small scales, direction of the angle. The DDM2, for example, map does not have. They're 5 degrees apart, these things. So so these are a reason why the cross correlation will go down, because if you have a wrong direction, okay? Second, even those directions, this stuff about the zero mode that I told you about is affecting the directions as well. I didn't go into this because I don't have such quantitative things to tell you, but these directions in this map also come from a ratio like that. So even those directions, you know, they have some systematics that we don't understand. So I think you really need to understand what is your expectation given this lack of knowledge on large angular scales and so on. Should you expect this template to actually correlate or not on degree scales, given that is the magnetic field sufficiently uniform, that has no orientation fluctuations on small scales? Also, the polarization fraction map is noisy, and so and it has these systematics of because of the zero level. So is it really correlating very well or not? So I just don't know the answer for a fact. I can tell you that you can do one exercise along the following lines, which I think is quite preliminary, so I will not show a transparency, but you can take this Q and U map scanned from SLab and assume it's the truth. And then say that you are producing a template of it in the same way as this DDM template is kind of being produced. So you measure this polarization fraction and you try to estimate directions on larger angular scales. You do that. And then you do Monte Carlos of kind of what is the cross correlation. These, I think, will settle the question. These are being done, and the preliminary thing that I can tell you, but is preliminary even, is that they're not so correlated if you do this. So you pay this, you see much lower cross correlation than you would naively think you should see. Not so different from what you see between the DDM2 and the DDM1 auto and cross. I don't want to say much more than that because it's Raphael's stuff.
So that's from digitizing our map?
No. This is not, because we don't have, the one thing that we can never do, well, he might try, who knows. And I think it's even more dangerous because the filtering that you have and anyway, so it's, no, but this is just the question. If I had I have a Q and U map from dust that I'm assuming is correct because it's my, just something that has more or less the statistical properties. And then I make a template a la DDM2 of that map, which is the dust map of the Q and U of them. And after I went through this procedure of measuring P and the angles, do they correlate? And the answer is that they don't correlate very well. I don't at the moment can tell you, well, I don't know how much this will, I mean, it needs to survive more scrutiny to understand what might be the reason for this. So for me, I think very interesting question at the moment. of the people that want to see if they can get to an answer faster than waiting for Planck is trying to understand to what extent the fact that the cross correlations are lower between these templates and the BICEP patch that are presented in the paper, the fact that those are low, what weight do they should they carry? I didn't talk about much because it's work in progress.
Just to use like the Finkbinder Davis-Schlegel maps and just assign some polarization to intensity fraction, that polarization to intensity fraction does not affect the cross correlation results because it's something you fit for with the cross correlation. Isn't that right?
I'm not. I mean, the polarization fraction is a map that in every pixel is different. So you really need to know the spatial structure of it. In order, if you get that wrong, the cross correlation will be.
But the overall amplitude.
The overall amplitude of the cross correlation, it will be then multiplied by a factor of whatever is wrong in the template. If it should be 2 or whatever. Yes.
Right. So.
Right. So
I'm actually fitting for it when I do that cross correlation. There's an overall amplitude that I'm. In other words, the uncertainty in that overall amplitude does not necessarily affect the significance of that I infer from the absence of a cross correlation.
I'm not sure what you're trying to get to. I mean, the only thing that I can say is that if I take the BICEP map and I take a map of the Earth and I cross-correlate it, the fact that I see 0,
yeah, I agree with that.
So it needs to be that the template is a good template, okay?
Yeah, that's a separate
so it's
question.
all about how good the template is. And this is a quantitative question. I gave you as much as I know about it. And I mean, I don't, it's very interesting. Unfortunately, is the kind of things we can do even less because we don't have the bias. I mean, it's just even more. So we can do pretend things like that to get a head around the, is it possible that the cross correlation, I mean, if you buy what these estimates from Amond, you would say the auto power is right where the signal is, but the cross correlation with this DDM2 map is like right down there. How is this even possible? That's the question I think you're asking. And of course, to the extent that the template is just a map of me, then it is reasonable. But of course, it's not that. It's better than that. But how much better than this quantity? I don't know. And I don't have the BICEP data, so I can do these mock things in pretending. But I think it's a very good question. I think it's a question that might lead to some more positive down the line.
Okay. So the other comment I had is there's some good news from your talk because you and I both had the same talk title, and I was worried that I was just going to say everything that she said, but no, I don't have to worry about that.
Any other question, comment? Eva.
Sorry, this is probably a much sillier question than the previous expert one, but if you were to take the opposite view and say you were really interested in dust, but there's this annoying, boring, inflationary possible, infection of the data, and so you ask yourself, do I have a convincing, statistically significant, detection of dust?
Yes.
You say yes? Or?
Of course. No. I'm going to take your question. Now, of course, I've heard this question from Eva many times, okay? And so this is just for the social media, okay? So I'll just exaggerate, okay? So I think, okay, if I am fair, the answer is we don't know that it's dust. All I want to say is that as far as I can see, the signal is consistent with what we might have expected based on those slides, dust to be. That's all I want to say. So if I was a dust person and my life, I'm Bruce Drain, I really care about the dust, does he know the polarization in emission of the dust? He doesn't, probably. It could be that it's inflation and it's much lower. It could be. And it's fine. Now, just to be on the provocative side, of course, dust exists, okay? It's there must be some prior, and I know that, and I've told you this already. I know you have a certain set of priors that are maybe different from like random people or me, but dust is there. You can see it. The gravity waves. Give me a break, okay? We got it. So if I multiply by that prior, then I would say once the order of magnitude is near the bicep patch, of course it's 100% dust. I think this is unfair, okay? But also I think that a 50-50 prior, okay, something in my gut doesn't tell me if I have to like wake up, dust just prior. Something is not the same, but it's just guts.
Okay. So it seems like the amount scaling result and all of this, data through keynotes and stuff is actually then significantly higher than was expected by pre-Planck models. Right. And so what's the cause of that? Is that just the polarization fraction is higher than we thought in general over the sky? Or is there more going on that I don't understand?
Yes. I think one should put a little bit of grain, understand exactly what we mean by those models pre-Planck, okay? I think as everything in astrophysics, these were not, like first principle calculations of what is to be expected in a galaxy if you wake up in the morning and then you do that. No, that's not what it goes. I mean, there's a lot of people working on models for the dust, but those models, the sizes and distribution in sizes of the dust grains, their composition, how they get aligned in the magnetic field, the ranges of temperatures they might have, all of those things are uncertain, and they go into some model that are fitted to data. And so what was and unfortunately, there wasn't so much data. The best data that there definitely was no data for how the dust emits in polarization at this frequency. We don't even have this data, I would argue, because Planck has the data, but we have like some joke data. There was some data from starlight polarization, so what you do there, you look at stars. The light of the stars is being absorbed by dust. It also gets a little bit polarized because the absorption is, if these dust grains are aligned, they preferentially polarize. This is measured on many lines of sight. And then you have to take a model to see if you know the polarization in absorption in the optical model, what is the polarization in the emission in the microwaves, and also it depends on the distribution of temperatures and so on. And so I think it's a fair statement that as many things in astrophysics, those models have factors of 2 uncertainty. And it's fine, it's usual. I mean, we usually plot things in log-log. The correlations are not even that good in the log-log, and we fit a line. So a factor of 2 in a log-log plot many times is very good. And then you go measure and you figure out more. So I think because there was no data, it's true that people expected or wanted, or I have no idea, lower levels, and it's indeed surprising if it's true that the level is higher. But I think the surprise was there in the SLab meeting. We haven't, for whatever reason, I didn't pay any attention to those. I would say I didn't pay attention except for one thing, okay? Another of these nagging problems in cosmology is this Planck lower amplitude. I mean, even at the time of the Planck meeting, we see the low temperature at low L compared to the model, okay? And I mean, if you look at the Planck papers, one thing that they are using that is not coming from them is the optical depth due to ionization that's coming from the polarization measured by WMAP. And I always thought, this part, okay, this is not so good for me to say online because my Princeton friends will see it. And, this is the part of WMAP which you might think that is the most uncertain because the polarization they were the first to see at this level. And so it could well be that there's some issue with tau, and then the peaks go down, everything is nice and happy, and we don't need a bubble nucleation and stuff like this. And in fact, the discussion in one thing that I remember is that in one of these discussions, it was shown the dust contribution to TE cross correlation compared to the models and so on, and you could see that there might be some dust contamination in TE, making the optical depth lower and fixing all these problems. I remember this discussion because, oh, look, if the dust is so large, then we can explain this other thing. And I was kind of happy because I guess my Princeton colleagues would have something wrong and people would throw them thing at them because they have some parameter wrong or something like that. And I would enjoy seeing that. But, sorry. But I don't know. So I remember that even there was some little discussion, oh, the dust might be. But then I forgot about it. And even when the BICEP was, I didn't even think about the dust.
So I'm still getting used to this new form of refereeing myself, and thank you all for your input. Had lots of it. It's a little bit hard to interpret how we should say we have estimated signal with a systematic and unknown error bar from an extrapolation from a slide that's comparable to the signal. It's hard to know how to quantify that or deal with it. So I agree with your first statement that the sane thing to do is to wait. And of course, in my case, as an experimentalist, that means that's my day job, to get to work and take better data and look at the data itself.
Yeah, I agree. In fact, I mean, just to make a sociological comment, and I think a lot of us think along these lines, we just go back and look at Penzias and Wilson discovery of the cosmic microwave background. What was the paper? Like excess temperature, okay? Had this just said excess B modes, blah, 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 and end of story, all the speculation that is going on from the theory side and everything would have happened anyway, and we would have been the ones that would be wrong and doing all of this, and people would claim, or I don't know I mean, for all I know, there's the B modes, but I mean, you would not be getting all the heat, and you would be in the, high above the ground, seeing all these people just fight against each other, making a fool of themselves like we do, the theorists, and doing all of this stuff, and you can take the high ground and say, look, I wait, okay? So I think this is I think, and I would be very happy, and I wouldn't have gone through like some sort of depression of what happened, this whole was going away, okay? I think this would have been better, in my opinion. And I think we would be in exactly the same position. We would not know, we would have to wait, and that's the same thing to do. We are all waiting, and that's yeah. I think the sociology, the Facebook, all of this is playing a big role in all of these discussions. It's not a good one in my opinion, but yeah, I don't know.
That is what our paper says, is the detection of polarization.
Yes, the title is perfect, and for the most part, yeah, I agree. Yeah, and I think at some level, I'm being unfair. Okay, I understand that. And the paper is but okay, if we are just talking, even though there's the internet, the paper is not the only thing. Okay, and that happened, and well, okay, we got some impression based on the whole package. Okay, and we should have looked at the paper maybe more carefully and see the caveats in the papers themselves, and yeah, that's okay.
Just had one minor thing about your summary before the summary.
Yes.
I think from listening to your talk, I would was this the one?
Yeah, no, it's before.
Previous one, that one. I would probably just reverse the third and first points. So, as you note, multiple evidence you showed that, and Raphael had done really great work. I shudder at the number of scientist hours that have gone into pixel scraping, which is, I mean, can't really claim moral high ground on that, but it's amazing. But you, as you showed, the level shown in the ESLab slides was consistent with the level of systematic error being shown. The signal to noise is not terribly enormous in the patch of interest. So you could read that same list of conclusions in sort of the other order and say, there's no reason to think that what we're doing is reliable, and you could instead phrase all of this as an upper limit on what dust could be and not a measurement of it. So just, you could view that list the other way. Then you would just say we don't have information as
Right.
opposed to it looks like this is dust. So you could say, all right, maybe you don't like DDM2, and that's reasonable, but
where
I think
did
what you've shown
where
me is a
did
lack
the-
of information
Yeah,
and not
but where
evidence
did
for something.
DDM2 come from? It came from here. So the only reason I'm giving this talk is because the paper was not written in the way of the moral high ground, okay? Now, fine. I mean, it's all sociology now, okay?
Yep.
It's so I think there's two things to take away from, or I hope to take away from what I'm trying to say. One is a sociological point that is kind of irrelevant, and it's a joke, and it's just to have some fun, okay? But I think the point is really we don't know, and it would not be surprising. In my opinion, it would not be surprising if a big part of the signal is just dust. I think I would not be surprised anymore. Maybe I would have been surprised before. I'm not surprised anymore. I hope that's not the case, okay? Maybe that would be the best summary. I would not be surprised anymore if that's the case. So,
Maria?
So if that's not the case and there is a mixture, as you said, does Planck know if they are sensitive to this kind of signal? Do they know that? I mean,
Well,
you know all the people that know everything, so
no,
you
I
must
don't
know if they know.
for the most part, I just know people that are now not knowing anything because they are not in Planck, they're not in BICEP, they're just anyhow. Yeah, I don't know. I think based on some of these systematic estimates that I was showing, one could doubt, one could be a little bit worried that maybe Planck, for the patches that are as clean as the BICEP1, might have some issues that we don't know, and I'm sure that by now they know if they will be able to do much better. And I think one point that I want to stress is that it's very important that this template or this other frequency which we're using to figure out if it's the CMB or not, that it's actually not just a measure of power, but the actual modes on the sky that are reliable. Because if you have to pay the cosmic variance error on those modes, is a very big error because it's a small patch on the sky. So it's very important that from Planck, if we're going to make I think, unless the dust is really small. If the dust is really small, it doesn't matter the cosmic variance. But assuming that the dust is not so small, it's like, say, a half of the total signal or something like this, on average over bigger patches of the sky. Unless one can be very precise on the actual shape of the map in that patch so that you don't pay the cosmic variance price, then it's a very big hit. And okay, by the Keck array, and they will also have the 100 gigahertz, and they will be able to do it much better and closer, and hopefully they can match those transfer functions very well, and they don't pay any kind of, and then we will know better. Yeah.
I'd like to point out that the first talk tomorrow morning will be by Olivier Dor, who is from the Planck collaboration. You have a question?
So just the Almant's scaling law is from actual.
Poor guy. I mean, just I don't know, Amont. This scaling. I mean, we are just taking this stuff that I don't know. It's just it's funny.
But it seems more robust than the. I mean, you can look at that plot, and so if you say, okay, well, he actually had the Planck data to make this 30% of the sky data point, right? So if BICEP had measured 30% of the sky, then it's perfectly valid to compare to his cleanest 30%. You know, if BICEP had measured the cleanest 30% of the sky, then it's totally valid to compare to that cleanest point on this, right? So the question is just what happens in the much cleaner portions of the sky.
Yes. Yeah. I think my summary of the situation is that for me, in fact, this scaling with its associated uncertainties is the most robust thing that the outside people can do at the moment, because it does not rely on digitizing a map. Presumably, we still are hoping that he checked a lot of things and that this was okay and so on. But I think based on data, it's the thing easiest to interpret. And then we are faced with the fact that we have to do a big extrapolation. And this is true. We have to do this extrapolation. There is this more or less of a power law. You can take that. We should. So I think the reasonable summary of our state of knowledge is to say this is more or less the case. We have to do this extrapolation. We have to make some estimate of these error bars, which is in some estimate, and that is the range. Unfortunately, this range is kind of in the middle of there, and so we don't know. That's the summary. For me, that's the summary.
Well, that's not even quite right, because the way the field was selected in the first place was based on the amplitude of the variance in the intensity, for the dust intensity. So you have to look at the variance.
Yes, but it would be, yeah. So of course, I mean, let's say it would be better. So there are other properties of the field, which you can imagine doing this against, and you might get a different answer when you do that. And I fully agree with that. I don't have those measurements as a function of that, and so I cannot do it. So I'm just saying this is the best that from such slides one can get, I think. I think this is a fair statement. I mean, there might be better properties to do this against, but unfortunately, you know, we don't have that information. And let me say that also another thing that is good about, it's true, it's an extrapolation, but I think given the systematics of Planck at the time, probably the measurements, and this might be a reason why this is cut at 30% and not going lower, the measurements are probably on those kind of, the signal is much stronger on those regions, so those kind of measurements are probably not going to change very much to what we will learn from Planck when they give this plot later. So that scaling is probably true against this. And so the whole question is, okay, the details of the extrapolation, can there be, and the variance around that average. This is just an average, and maybe there's big fluctuations, I don't know, and it may well be that because of another reason, the BICEP is on the low side of that variance when this scaling relation is fully known to us. I just don't know. I hope that's the case.